We'll start thermodynamics, Thermodynamics-1. So, there are two chapters in thermodynamics. So, what is thermodynamics? So, the branch of science that deals with the study of different forms of energy and their interconversion is called thermodynamics. Some basic terms and concepts. So, in thermodynamics we always call system and surroundings. So, what is system? System is a specified part of the universe. Here you can see blue color, that is under observation, is referred to as a system. So, what is universe? The remaining part of the universe which lies outside the system boundary. This is the boundary, system boundary, is referred to as surroundings. There are different types of system like open system. So, open system means a system which can exchange matter as well as energy with its surrounding is called open system. So, we have a system here and we have surroundings here. When there is both matter and energy exchanges are permissible between system and surroundings, we call the system is open system. Next comes closed system. Closed system is a system that can exchange energy but not matter with the surroundings is called a closed system. And then we have isolated system, and a isolated system that can neither exchange matter nor energy with its surrounding is called an isolated system. So, open system is when both energy and matter exchanges are permissible between system and surroundings. Closed system is matter exchange is not permissible, but energy exchange is permissible, and isolated system when neither matter exchange nor energy exchange is permissible. And next we discuss extensive and intensive property. So, extensive property means the properties of the system whose value depends upon the amount or mass or size of the substance present in the system are called extensive properties. For example, mass, volume, surface area, internal energy, enthalpy, entropy, free energy, heat capacity, all are extensive properties. Intensive property, the properties of the system whose value is independent of the amount or size of the substance present in the system are called intensive properties. For example, temperature, pressure, viscosity, surface tension, dielectric constant, specific heat capacity, vapor pressure, refractive index, etc. So, as mentioned before, so open system means both energy and matter exchange are permissible here. Closed system only energy exchange permissible. Isolated system neither matter nor heat exchange is permissible. Then concept of internal energy. So, what is internal energy? Every substance possesses a definite quantity of energy which depends upon factors such as chemical nature of the substance, temperature and pressure. This is known as an intrinsic energy or internal energy. It is the sum of all forms of energy stored in atoms or molecules. The absolute value of internal energy, we denote it as U, cannot be calculated. So, absolute value of internal energy cannot be calculated. Hence, we are interested in the change in internal energy which occurs during chemical reactions. So, we actually focus more on change in internal energy rather than the absolute value of internal energy. Let UA and UB the internal energies in states A and B respectively. Then the difference between the internal energies of the two states is delta U, if we say, that is UB minus UA. For chemical reactions, the change in internal energy may be considered as the difference between the internal energy of the products and the reactions. So, delta U is U products minus U reactants. If delta U is negative, means U product is less than U reactant, and if delta U is positive, means U product is greater than U reactant. Thus, U is a state function, meaning it depends only on the initial and final state and is independent of the path. So, suppose we have a system here, system A, and we have system B. So, system A is our initial state and system B is our final state. So, if we go system A to B via this one, this is path 1 and this is your path 2. So, there are two different paths. So, delta U is your UB minus UA, because A is our initial state, B is our final state. So, internal energy of the final state is UB and internal energy of initial state is UA. So delta U is UB minus UA. So it will be the same for both the paths, because U is a state functions. So irrespective of the path we take from same initial state to same final state, then change in internal energy will always be the same. Then concept of heat. So what is heat? So heat is a form of energy. So the energy exchange is the exchange between the system and surroundings as heat when there is temperature difference between them. So when there is a temperature difference between the system and surroundings, we get heat. This process continues till both the temperatures become equal. Okay, so if temperature of both system and surroundings are equal, then there is no exchange of heat, or we will not get any heat there. So here is a schematic diagram. If you see, it's the system is hotter than the surroundings here. So temperature of the system is higher than the surroundings. So heat will go from system to surrounding. So system will lose heat here. So here Q is negative. And here this is the system is colder than the surroundings. So heat, it will take heat, or the system will gain heat from the surroundings. So Q, heat you denote by Q is here positive. So when system gains heat, Q is positive, that is a convention. When system loses heat, Q is negative, this is also a convention. For example, suppose we take water at a temperature TA in a container having thermally conducting walls, enclose it in a huge heat reservoir at temperature TB. The system will absorb heat from the reservoir, and the temperature difference can be used to measure the heat absorbed. So if we measure the temperature difference between TB and TA, TB minus TA gives the heat. Q is positive when heat is transferred from the surroundings to the system, means when system gains the heat, as I mentioned, Q is positive, and it is negative when system loses the heat. So what is work? Again, work is another form of energy. So work is said to be performed if the point of application of force is displaced in the direction of the force. Or in other words, we get force when there is an imbalance force between, we get work when there is an imbalance force between the system and surroundings. If F is the force and dl is the displacement of the point of application in the direction of force, then the work done is given W is force times displacement, we already know. So F is the force and dl is the displacement. So what is pressure volume work? So work, we get pressure volume work when there is a change in volume. Consider a cylinder containing a mole of gas with a volume Vi, and the pressure inside is P. It is fitted with a frictionless, weightless piston. Let the external pressure acting on the piston is P external. Here, this is the volume of the initial volume of the gas Vi, and if we apply pressure, a P external pressure, when P external is greater than P internal, then volume will decrease here. This is the final volume, and the height will change from Hi to Hf, you can see. This is the change in height. So let the external pressure acting on the P external, if P external is greater than P, as if external pressure is greater than the internal pressure, the piston is moved downward like this, and cross sectional area A from the height Hi to Hf. So initial height was Hi and the final height was Hf, and A is the area of the piston. So what is the change in volume here? Change in volume is your delta H is your Hi minus Hf is the change in volume here. So we get A times delta H. Yeah, so change in volume is A times Hf minus Hi, as I mentioned. So yeah, F is the final height, Hf is the final height, Hi is the initial height. So change in height is Hf minus Hi. So if W is the work done on the system by the piston, so W is P external minus delta V. So we get W is minus P external times delta V. So this is the work done of the system. Now pressure volume, if P external is less than P. So in previous case we considered P external is greater than P. Now if we consider P external is less than P, work will be done by the system on the surroundings. So in that case, Vf is greater than Vi, so W will be negative as per the convention. So when work done by the system, the convention is the W will be negative, and when work done on the system, the work done W is positive. This is by convention. So if compression works, in compression work, Vf is less than Vi and W will be positive. So for expansion work, delta V is positive, so work done is negative. For compression work, delta V, a change in volume, is negative, so W will be positive. Let us suppose the pressure or volume is not constant at every stage, then the work done will be the area under the curve and can be summed over this. So if this is the case, then we get work done is sum over P external times delta V. So we have to calculate area under this. So the volume is changing from V1 to V2 here. So we need to calculate area under the curve here. Then we discuss first law of thermodynamics. So first law of thermodynamics states that energy can neither be created nor destroyed, although it can be converted from one form into another. This holds good for chemical reactions too. Energy may be absorbed or evolved in the reaction, but the total energy of the reacting system and the surroundings remains constant. Now mathematical expression of the first law of thermodynamics. Let us consider a system whose internal energy is U1. Now if the system absorbs heat means Q is positive here. So absorb Q amount of heat, then the internal energy of the system becomes U1 plus Q. So we have the internal energy U1, now system absorbs heat of amount Q, so we get the internal energy changes from U1 plus Q. Now if W is work done on the system, then the internal energy further increases to U2. Now work done on the system here, so W is positive. So we get U1 plus conservation of energy, so U1 plus Q plus W gives you U2. So U2 minus U1 gives you Q plus W, or U2 minus U1 is nothing but change in internal energy. So change in internal energy equals to heat added to the system because Q is positive, and W means plus W means work done on the system. If a system does work on its surroundings, its internal energy decreases. In that case, W is taken as negative. Now, if Q amount of heat is added to a system and W is work done by the system, then the change in internal energy becomes Q plus minus W, so Q minus W. So change in internal energy here is heat added to the system and work done by the system. The above relationship is the mathematical statement of the first law of thermodynamics. So we consider mainly this expression, this one. Okay, delta U is Q plus W. Substituting the value of W from 9, we get delta U is Q minus P external times delta V. So if the process is carried out at constant volume, so delta U is, so external, there is no change in volume, so B is constant volume process. So P external times delta V gives you 0. So delta U is nothing but Q at constant volume, so you can write QV. So change in internal energy is heat absorbed or evolved in a reaction at constant volume. Then we talk about reversible and irreversible processes. A process or change is said to be reversible if it is brought out in such a way that an infinitesimal change could at any moment reverse the process. A reversible process proceeds infinitely slowly by a series of equilibrium states such that the system and the surroundings are always in near equilibrium. The processes that are not reversible are called irreversible processes. We can relate work to the internal pressure of the system under reversible conditions if volume changes from V1 to V2. So for reversible process, W reversible is V1 is the initial volume, V2 is the final volume. So they have minus sign, P external times dV. Now external pressure is slightly different from internal pressure. So that's why the external pressure is P. If we say internal pressure is PIN, then P external is PIN plus minus dP here. So if we substitute it, we get this expression. Now this quantity dP times dV is very, very small, so we can actually neglect this one. So we get W reversible is minus V1 to V2 P internal times dV. This is general expression. So and this expression is valid for all gases irrespective of gas molecule. This is general expression. Now, if we consider ideal gas, so we can write P internal is P, so P internal is nothing but nRT by V. So, if we substitute the value of P here, P internal as P by nRT by V, we end up with this expression W reversible is minus nRT ln V2 by V1, and then this is log E base. If we consider log 10 base, we get this expression for work done in reversible process. For isothermal changes in an ideal gas, for example, expansion into vacuum. So, expansion into vacuum means when external pressure is 0. So, when external pressure is 0, so the work done we know minus P external times delta V. So, work done will be 0, that is why you get work done is 0, and as P external is 0 as I mentioned, and at constant temperature, so Q is also 0, so delta U is 0. So, you need to remember that for ideal gas, U is function of temperature only. So, when temperature is constant, so there is no change in internal energy. So, for isothermal process, for an ideal gas, delta U is always 0. So, if we first law of thermodynamics, so from first law of thermodynamics, what do we know? We know delta U is Q plus W. So, delta U is 0. So, Q is minus W as delta U is 0. That is why we are getting here. So, Q is minus W. Now, the value of W is minus P external times delta V. So, delta V is Vf minus Vi. So, we get Q is P external times Vf minus Vi. This is for irreversible process. For reversible change, Q is minus W. This is also valid, but expression for W here is this one, minus nRT ln Vf by Vi, and you have the minus sign one more here, so we get plus sign here. So, W for irreversible process is minus P external times delta V, and W reversible process is minus nRT ln Vf by Vi for isothermal process. Okay. So, we get the expression for Q like before. Now, for adiabatic change, so for adiabatic change, there is no change in heat, so Q is 0. So, if Q is 0, from the first law of thermodynamics, we write delta U is W adiabatic, so delta U is W here. Next, we discuss enthalpy. So, what is enthalpy? When a chemical reaction takes place in an open atmosphere, there may be a volume change, but the pressure remains constant, that atmospheric pressure. So, in case of internal energy we can measure at constant volume process, for constant volume process. Okay, so, if we go back and check it, we see that okay, so delta U is QV. So, change in internal energy is nothing but heat for constant volume process, but most of the reaction that we carry out in the laboratory, that is at constant pressure, not at constant volume. So, we need to define another quantity, okay, so that can actually help us to understand the reaction better. That is why the concept of enthalpy comes here. So, that is why it is said that when a chemical reaction takes place in an open atmosphere, there may be a volume change, but the pressure remains constant, that is atmospheric pressure. So, enthalpy comes when pressure remains constant. To study the heat changes for reaction at constant pressure and constant temperature, a term called enthalpy has been introduced. Just what I mentioned now. So, delta U we know is Q plus W. So, Q is at constant pressure process, Q is Qp, and external W is minus P delta V. So, we get delta U is Qp minus P delta V. Now, let us represent initial and final state by subscript 1 and 2. So, delta U is U2 minus U1. So, Qp minus P V2 minus V1. So, if you rearrange this one, we get Qp is U2 plus P V2 minus U1 plus P V1. So, we can define another thermodynamic function enthalpy, H is U plus PV, so, and then equation 28 here, it becomes Qp is H2 minus H1 gives you delta H. Thus, H is also a state function like U, H is also a state function and is the sum of the internal energy. You see sum of the internal energy and the product of pressure and volume of the system. So, H is nothing but U plus P times V. For a chemical reaction, if delta H reactants and H products are the enthalpy of reactants and product respectively, the change in enthalpy is delta H is del H products minus H reactions. Now, what is the significance of enthalpy change, internal energy change, and the first law of thermodynamics? According to first law of thermodynamics, delta U is Q plus W. If we include pressure volume work done by the system, so delta U is Q minus PdV. So, if we rearrange this one, we get Q is delta U plus P delta V. Now, if the process is carried out at constant volume, is delta U is QV. Now, the change in internal energy is equal to the heat absorbed by U at constant volume and at constant temperature, that we just discussed. Now, enthalpy H is U plus PV. So, delta H is U, if we take delta, so delta H is delta U plus delta PV. So, delta H gives you delta U plus P delta V plus V delta P. Now, at constant pressure process, delta P is 0, right. So, if delta P is 0, so delta H is delta U plus P delta V. Now, delta U plus P delta V, this is nothing but Q, right. So, delta U plus P delta V is nothing but Q. So, we write delta U is delta H is Q minus P delta V plus P delta V, so gives you Q. So, delta H is QP. The change in enthalpy is the measure of heat absorbed or evolved at constant pressure. So, we can sum up, if Q is the amount of heat absorbed by the system, then QV, when volume is constant, so heat absorbed at a constant volume process gives delta U, and heat absorbed at constant pressure process gives delta H. So, what is the significance of enthalpy change, internal energy change, and first law of thermodynamics? Consider a chemical reaction going from A to B at constant pressure P. So, A goes to B. If HA is the enthalpy of A and HB is the enthalpy of B, so delta H is HB minus H. Again, we know H is U plus PV. So, the HA gives you UA plus PV, because pressure is constant, we are considering enthalpy here, and HB is UB plus PV. So, delta H means HB minus HA. So, if we write, so you get UB plus PVV minus UA plus PVA. So, if you rearrange this, we get delta H is delta U plus P delta V. Now, what is P delta V? Because PVA equals to NA at T, PVV equals to NB at T. So, if we subtract them, we get PVV minus BA gives NB minus NA types at T. So, P delta V is delta NG at T, where delta NG is the change in the number of gaseous moles of products and gaseous moles of reactants. So, we get delta H is delta U plus delta N G at T. Okay. So, in change internal energy change at constant pressure delta H is energy change at constant volume delta U plus change in the number of gaseous moles times at T. So, remember here that delta N is nothing but delta Ng here, change in gas, for gas only. Why it is gas? So, if we consider suppose a reaction like N2 plus 3H2, these are all gases, gives 2NH3, again it is gas. So, delta N for this process is 2 minus 1 plus 3, so gives you minus 2. Now, you consider another case H2 gas plus half O2 gas or 2H2 gas plus O2 gas, hydrogen and oxygen, they gives water H2O liquid. So, we get delta N here is 2 times, now this delta N comes from the volume. Okay. So, this is your molar volume of water H2O liquid. Okay. So, this 2 comes from molar volume of reactant, or this is for your product and this is for reactant. So, delta N here is, we consider 0 minus, because this is liquid state, 0 minus 2 plus 1, so gives you minus 3. Now, why you consider 0 here for liquid or solid? Here it is like this delta N comes from delta V. You see delta V, it comes from this delta V term or change in volume. Since the molar volume of liquid or solid is much smaller than molar volume of gas, so we can actually neglect the molar volume of liquid and gas when compared to water or when compared to gases. So, we can actually neglect molar volume of liquid or solid compared to gas. That's why we don't consider here the liquid. For example, for liquid water, the molar volume is 18 milliliter, you know. For 1 mole of water in liquid state, we get volume is 18 ml. Whereas in the gaseous state, 1 mole is for at STP is 22.4 liter. So if we compare 22.4 liter and 18 ml, so we can actually neglect 18 ml. That's why we do not consider, we consider change in number of moles for gaseous molecules only when we calculate delta H by using this expression delta H equals to delta U minus delta Ng at T. Next we discuss what is heat capacity. Heat capacity is defined as the amount of heat required to raise the temperature of the system by 1 degree. So more the amount, you need more heat to raise 1 degree. That's why heat capacity is an extensive property. Okay, it depends on the mass of the system. But molar heat capacity is intensive property, because when we talk about molar heat capacity means we are defining that amount of substance. So molar heat capacity is an intensive property and heat capacity is an extensive property. It can be simply calculated by dividing the heat absorbed by the increase in temperature. So if Q is the amount of heat required to change in temperature is delta T, then heat capacity C is Q by delta T. His heat capacity is of two types. Heat capacity determined at a constant volume Cv and heat capacity determined at a constant pressure Cp. Okay, so heat capacity, another thing is heat capacity is a path function. Okay, heat capacity is not a state function, because whether the process is taking place from the same initial state to same final state at constant volume or at constant pressure, we know the value of Cv and Cp are different. So in general, heat capacity C is path function. But when we talk about Cp or Cv, then heat capacity is a state function, because we are defining the path when we talk about Cp and Cv. So relationship between Cp and Cv, at constant volume heat absorbed, we know Qv is delta U, right. So delta U is nothing but Cv times delta T. At constant pressure heat absorbed is Qp, we call Cp is times delta T or delta H, right. So again we know for ideal gas delta H is delta U plus P delta V. So delta H equals to delta U plus delta RT. So delta H is delta U plus R times delta T. Now if we substitute everything, so we get Cp delta T is Cv delta T plus R delta T. If we divide both sides by delta T, we get Cp equals to Cv plus R. So Cp minus Cv equals to R, or the gas constant. This is applicable for 1 mole of an ideal gas. Similarly, for n moles of an ideal gas, Cp minus Cv is n times R. Hence the two heat capacities are not equal. Cp is greater than Cv, because Cp is at constant pressure process. Okay, so heat capacity at constant pressure is Cp and heat capacity at constant volume is Cv. So for Cp means we need more heat to raise 1 degree temperature, because some amount of heat is being utilized to overcome or to do some work. So you need more heat to raise 1 degree Celsius or 1 degree Kelvin. That's why Cp is greater than Cv.